We are looking at SimVLA today, a simple VLA baseline for robotic manipulation by Yongkai Luo and the team at Frontier Robotics, published February 2026.
And honestly, it is a massive wake-up call for the entire field.
Yeah. The central thesis is basically that we have completely over-engineered robotic control.
Right, because the industry has just been chasing these massive 7 and 8 billion parameter models.
It's like OpenVLA and Pi0.
Exactly, stuffing them with complex 3D priors and all these memory modules. But SimVLA achieves state-of-the-art performance with a streamlined 0.5 billion parameter model.
Which is just a huge efficiency gap.
It really is. I mean, they hit a 98.6% average success rate on the LIBERO simulation benchmark, beating those much larger models.
They do it not by inventing some crazy new architecture.
Right, they just strictly decouple perception from action, using an off-the-shelf Florence 2 VLM for vision and a very vanilla transformer action head using flow matching for control.
But the real story here for the ML engineers listening is the training recipe. The authors claim the gains come from 3 silent drivers:
global data shuffling, strict normalization, and a very specific learning rate multiplier.
They basically prove that a simple architecture with rigorous data hygiene beats a complex architecture with standard training.
Yeah, it sets a totally new lower bound for the field. If your complex new model can't beat this baseline, you haven't made progress.
Welcome back to AI Paper Podcasts. So that was the 1-minute summary for you guys, but we really need to unpack this.
Because the implications for how we train robot policies going forward are just huge.
Let's start with the context of all this. Why do the authors feel the need to publish what is essentially a baseline paper in 2026?
Well, because the field is in a bit of a crisis, to be honest.
Right.
If you've been following RCEF for the last 18 months, you've seen the trend. It's just more is better. Every week there's a new state-of-the-art paper.
And the architecture diagram always looks like a bowl of spaghetti.
Yes, exactly.
Yeah.
People are adding explicit 3D point cloud encoders and recurrent memory banks and temporal attention mechanisms.
And usually those papers show, what, a 2 or 3% improvement over the previous state-of-the-art?
Right. But here's the problem, and it's what we call the attribution problem. Let's say I invent a super spatial VLA, and I add a complex 3D module to it.
Okay.
But in order to get it to train properly, I also tweak the learning rate schedule. I change how I batch the data. Maybe I use a slightly cleaner data set.
So when you get that high score...
Is it the 3D module? Or was it just the learning rate?
And nobody usually goes back to check.
Exactly. We just assume the complexity was necessary. So SimVLA is the counter-argument to all of that.
They're essentially saying, let's strip all of that away.
Yeah. They built a model that is aggressively simple to serve as a transparency tool. They just want to know how good a vanilla transformer can be if we just treat the data right.
That is a great mission. So let's actually look at the architecture they settled on. They call it an encode once strategy.
Right.
How does that differ from something like OpenVLA?
Well, in a monolithic VLA, like OpenVLA, the vision capabilities and the action generation are deeply, deeply entangled.
So they're all mushed together.
Yeah, and often you're running that massive 7 billion parameter backbone for every single step of the robot's movement.
Which is computationally incredibly heavy.
Super heavy. It's why you need a rack of H100s to run them.
Right.
SimVLA decouples this entirely. They use Florence 2, which is a fantastic and very efficient vision language model, and they use it purely as a perceiver.
So it just looks at the image in the instruction.
And it encodes them into tokens. It creates a static representation of the scene.
And it only does that once per step.
Correct. It essentially says, okay, I see a mug on the table and the user wants me to pick it up. And then it passes that understanding over to the action head.
And the action head is the vanilla part you mentioned earlier.
It is as vanilla as it gets. Literally a standard transformer encoder. Just self-attention.
No cross-attention bridges or fancy routing.
Nothing. It just takes the vision tokens and concatenates them with the robot's proprioception.
Proprioception being where the arm is currently located, right?
Yeah, the joint angles and all that, plus the time embedding.
Okay, I want to double-click on the control mechanism, though, because they aren't using diffusion.
No, they aren't.
Which is super surprising, right? Because diffusion policies have basically been the gold standard for robotic control for the last couple of years. Why switch to flow matching?
Diffusion is really powerful, but it brings baggage. Think about how diffusion works. You start with pure Gaussian noise.
Right, and you iterative denoise it.
Exactly. You iterative denoise it to find a valid action, but it's a stochastic process. It's probabilistic. You are essentially guessing your way through the fog to find the right path.
And that takes a lot of compute. It's slow.
It is slow at inference time because you need so many steps. And honestly, it can be unstable to train. Flow matching is completely different.
How so?
It learns a deterministic vector field. Instead of guessing through the noise, it learns a direct flow or a current that pushes the noise distribution straight into the data distribution.
So it's more like following a map than guessing a shape.
That is a really good analogy, yeah. Technically, it allows them to use an ODE solver with Euler integration steps to find the action.
Which sounds complicated, but the result is what matters.
The result is that training is much more stable and inference is significantly lighter, which is a big reason they can run this model on consumer hardware.
Which we are definitely going to touch on later because the efficiency stats are wild.
Oh, yeah.
Okay, so that covers the simple part of SimVLA. But the authors are pretty adamant that the architecture is actually secondary.
Yes.
They dedicate a huge chunk of the paper to what they call the silent drivers of performance.
This is the vegetable section of the paper.
Yes, eat your vegetables, ML engineers. Because this is the part I really want you to pay attention to. This is where the magic actually happens.
It's not sexy, but it is what makes it work. They ran all these ablation studies where they turned off these specific implementation details.
And the performance didn't just drop right, it completely collapsed.
It absolutely tanked.
Let's go through them one by one. Driver number 1 is data shuffling. Now, everyone listening knows you have to shuffle your training data. Why is this a headline finding?
Because in robotics, data isn't independent. If you're training a standard ImageNet classifier, right, a picture of a cat does not predict the next picture of a dog.
They're completely separate.
Exactly. But in robotics, you are training on trajectories. So frame 50 is highly, highly correlated with frame 51.
Right, it's time series data. It's a video, basically.
Exactly. And if you feed that data into the model sequentially, like here's the full video of picking up the cup in order...
The model just overfits to that specific sequence.
Yes, it learns the autocorrelation. It thinks, oh, well, if the pixel was at X in the last frame, it must be at Y in the next frame, rather than actually learning the underlying physics or the intent of the action.
So it's literally memorizing the movie instead of learning the skill.
Precisely. So SimVLA uses global shuffling. They break that temporal correlation entirely during training.
They just mix every single frame up from all the different trajectories.
Yes. And when they turned this off in the ablation study, the success rate on the LIBERO benchmark went to nearly 0 on some tasks.
Almost 0. That is wild to me. You could literally have the smartest architecture in the world, but if you don't shuffle the trajectory data globally, you just get a brick.
It really highlights that for a lot of failed experiments in the past, maybe the problem wasn't the architectural idea at all, it was just the data loader.
Man, that is a painful thought for anyone who abandoned a project last year. Okay, driver number 2 is normalization. Again, this sounds like basic housekeeping.
It is housekeeping, but it's the kind of housekeeping that keeps the house from burning down.
Fair enough.
You have to remember what we're feeding into this transformer. On one side, we have high-dimensional vision embeddings coming out of Florence 2.
Right.
And on the other side, we have proprioceptive data, the joint angles at the robot arm, which might be measured in radians or millimeters.
The scales are completely different.
Radically different. If you don't normalize the action space and the proprioception to the training set statistics using the mean and standard deviation, the optimizer just gets incredibly confused.
Because it doesn't know how to weigh the inputs.
Exactly. It might think a 0.1 change in radians is huge or tiny, depending on the random initialization.
And what was the result of skipping this step in the ablation?
The average success rate dropped from roughly 98% down to 12%.
It's from 98 to 12. That is a catastrophic failure mode just for skipping basic normalization.
It proves that the transformer cannot just learn its way around bad scaling. You have to prep the inputs for it.
Okay, driver number 3. This one is a bit more of a pro tip for all the fine-tuners out there, the VLM multiplier.
This is crucial. This addresses the catastrophic forgetting problem.
Right, because Florence 2 is pre-trained on the internet.
Exactly. It already knows what a cup is. It knows what the color red looks like. You want to adapt it to the robot's specific camera and specific tasks, but you really don't want to wipe out all that incredible pre-trained knowledge.
So you have to slow down the learning process for that specific part.
Yes. They found that if you train the whole model at the exact same speed, the VLM overfits to the robot lab environment.
It just forgets the rest of the world.
Exactly. It loses its general visual capabilities. So what they did is they applied a 0.1x multiplier to the learning rate for the VLM backbone.
Okay.
So the action head trains at full speed at 1.0, but the vision model trains at 1/10 speed.
And did they test doing it at full speed to see what would happen?
They did. Setting the multiplier to 1.0 caused the success rate to drop down to 44%.
Wow. So the model effectively became dumber because it was learning too fast.
It overrode its own foundational knowledge.
It's just fascinating. Look at these three things, right? Shuffling, normalization, learning rate multipliers. And they account for a much bigger performance delta than the difference between a 0.5 billion parameter model and a 7 billion parameter model.
That is the ultimate takeaway here. We have been attributing intelligence to scale when we really should have been attributing it to engineering rigor.
So let's talk about the actual results, because the proof is in the pudding. They benchmarked this heavily on the LIBERO simulation suite. How did this, David, compare to the Goliaths?
It was a clean sweep, honestly. On the LIBERO spatial object and goal suites, SimVLA was hitting near 99% success rates.
Which is basically perfect.
Yeah, it outperformed OpenVLA OFT, which is 7 billion parameters, and it outperformed the reproduced version of Pi0.
The result that really surprised me, though, was LIBERO long.
Ah, yes.
Because this is the benchmark for long horizon tasks, right?
Okay.
Things like open the drawer, then put the item in, then close the drawer.
Right, it's a multi-step process.
And usually the assumption in the field is that you need an explicit memory module for this.
You need a recurrent neural network or a specialized history buffer so the robot actually remembers that it already opened the drawer.
But SimVLA doesn't have any of that. It is literally just a feed-forward transformer.
And yet it scored 96.4% on LIBERO long.
How does that even work? If it has no memory module, how does it know it's on step 2 of 3?
It's a great question. It strongly suggests that explicit memory might actually be redundant if your perception is just good enough.
Because it can just see what's happening.
Exactly. If the robot looks at the scene and sees an open drawer and a block in its hand, the only logical next step is put the block in the drawer.
The state of the world literally is the memory.
The state of the world is the memory. A strong enough base policy mimics memory just by being highly accurate in the present moment.
So we've been building all these complex memory modules to compensate for the fact that our policies were just really bad at reading the current state of the room.
Pretty much, yeah.
Now, they did run into some limitations, we have to be fair. They ran LIBERO Pro, which is a robustness benchmark.
This is a really good honesty check for any model. It actively messes with the environment. It changes lighting textures, object positions.
And how did SimVLA hold up?
Well, it is incredibly robust to semantic changes.
Meaning what exactly?
Meaning you can change the color of the table, you can change the lighting, the background, and it still works perfectly.
Which makes sense because Florence 2 is doing the heavy lifting there.
Exactly. That's Florence 2 pulling its weight.
Right.
But positional robustness.
Right, if you move things around.
That's where it hurts. If you teleport the target object to a location that is way outside the training distribution, the performance drops off pretty sharply.
But looking at the charts in the paper, everyone failed that test, didn't they?
Correct. OpenVLA failed, Pi 0.5 failed. SimVLA actually performed slightly better than Pi 0.5 on task robustness.
So it's an industry-wide problem.
It shows the field as a whole just hasn't solved the out-of-distribution location problem yet. But the point stands, right? 7 billion parameters didn't solve it either.
Right. Okay, moving out of the simulator, let's talk real world. They deployed this on the Galaxia R1 Lite, which is a mobile bimanual robot.
And they used a strict zero-shot protocol for this.
Which is the gold standard for evaluation, right?
Absolutely. They trained on the Galaxia dataset, but tested it on completely held-out scenes. Rooms and physical setups the robot had never, ever seen before.
With no fine-tuning at all.
Zero fine-tuning.
And what kind of tasks were they having it do?
Really complex manipulation. Things like put the pen in the holder, which requires a lot of fine precision. Fold the clothes, which is notoriously hard for robots because cloth is highly deformable.
Oh yeah, folding laundry is the holy grail.
And simpler things too, like wipe the desktop or pick up garbage.
How did the performance actually match up to the big guys?
It matched the performance of Pi 0.5. And for context for those listening, Pi 0 is a model from a lineage of major labs. We're talking physical intelligence, Google DeepMind style research.
And SimVLA, this tiny little model from Frontier Robotics, basically stood toe-to-toe with it.
Toe-to-toe. on held-out scenes in the real world.
But the killer stat for me in this whole paper is the efficiency. We talk about democratizing AI all the time on this show, but usually that's just a buzzword.
Yeah, here the numbers are stark.
Let's lay it out.
To train OpenVLA, you need about 62 gigabytes of VRAM per GPU.
Which basically means you are renting A100s or H100s from a cloud provider.
Yeah, you're talking a serious enterprise budget.
And SimVLA.
SimVLA trains on 9.3 gigabytes of VRAM.
9.3 gigabytes. I mean, I have a 4090 in my desktop sitting right here that has 24 gigs. I could literally train two of these models at the exact same time.
You literally could, and that is the point. This brings state-of-the-art robotic policy training completely within reach of university labs, startups, and even individual researchers in their garage.
You just don't need a massive compute cluster anymore.
Not if you do the engineering right.
That accessibility also links back to the modularity aspect we touched on earlier, right?
Yeah.
Because they decoupled the vision, you aren't stuck with Florence 2 forever.
Exactly. And that is the real strategic advantage of the Encode Once design. If Meta releases Llama 4 Vision next week, or OpenAI drops some incredibly new edge-optimized vision model,
You can just swap out the backbone.
you just plug in the new eyes.
You don't have to retrain the whole architecture from scratch.
No, you don't. You plug in the new VLM, maybe do a brief warm-up training to align the embeddings.
Remembering that 0.1x multiplier, of course.
Of course, don't forget the multiplier. But yeah, suddenly your robot is just smarter. Whereas in a monolithic model, upgrading the vision capabilities means retraining the entire 7 billion parameter beast from scratch.
Which takes months and millions of dollars.
Exactly.
I really like the concept the authors proposed near the end of the paper of the lower bound. It feels like a direct challenge to the research community.
It is throwing down a gauntlet. They are saying to the field, stop showing us your fancy architectures unless you can beat this baseline first.
Right. If you publish a paper with a graph neural network and a 3D voxel fusion module, and you get 98.6% on LIBERO.
Well, SimVLA already did that with a plain vanilla transformer, so your complexity added absolutely zero value.
It forces researchers, to be honest. You have to prove that your smart module is actually doing work and not just hiding the fact that you finally figured out how to fix your data shuffling.
It completely raises the bar for evidence. Future papers are going to need to show they matched SimVLA's rigorous training recipe.
Silent drivers.
Right, they have to implement those silent drivers and then show they still improved on the baseline.
It seems like 2026 is rapidly becoming the year of boring is better.
I love that.
We see it in LLMs, right, with the extreme focus on data curation over parameter count. And now we're seeing it right here in robotics.
It's a true sign of a maturing field. In the early days of any AI subfield, you make huge gains by inventing wild new structures. But in the mature phase, you make gains by refining the process.
Optimizing the pipeline.
SimVLA is the signal that vision language action research is finally growing up.
So summarizing all of this for you guys today, SimVLA proves that rigorous engineering data hygiene normalization hyperparameter tuning fundamentally beats flashy architecture. It is quite literally a 0.5 billion parameter David beating the 7 billion parameter Goliaths.
Absolutely.
I want to leave everyone listening with a final thought on the deeper implications of this, because we have spent years assuming that for a robot to act intelligently, to look at a messy kitchen table and actually clean it up, it needed a massive brain inside its own head.
Right. We thought the control policy itself needed to be this giant, complex reasoning engine.
But SimVLA is doing complex, dexterous manipulation with 500 million parameters. That is microscopic by modern standards. It's practically a reflex arc.
It really begs the question, doesn't it? Are we reaching a point of diminishing returns for intelligence in low-level control?
Maybe the robot's physical body doesn't actually need to be smart.
Maybe it just needs to be a very efficient spinal cord.
A tiny spinal cord for the body, and maybe a big VLM running in the cloud for the high-level planning.
Exactly. If we can solve high-fidelity manipulation with a lightweight deterministic model, we can just offload the deep reasoning to a separate system entirely.
We don't need to cram the philosophy degree into the hand that holds the screwdriver.
That is a perfect way to put it. The separation of concerns is the future.
It is a fascinating shift in how we think about embodiment. Well, that is all we have time for today on AI Paper Podcasts. For all the ML engineers listening to this, seriously, go check your data shuffling and normalization settings right now. You might just get a free soda bump out of it.
And please keep that learning rate multiplier low.
Always. Thanks for joining us today. We'll catch you on the next deep dive.